Hey there, this is a late night edition of Kung Fu Physics. We are working our way through practice physics GRE problems. The one I want to do tonight I actually was going to do last week and I put it off. It's kind of an annoying problem that you can confuse yourself on if you think too much about it. But it's not hard, it's just annoying. It's number 30 off of the 1996 exam. 3096. It looks like this. Let's go ahead and do it. As usual, I scan the answers. It looks like it's got a bunch of fractions as the answers, and we're going to go ahead and take a quick look at that diagram and then go into the problem. I'll read the text. Number 30. An open-ended U-tube of uniform cross-sectional area contains water. Density 1.0 grams per cubic centimeter. Standing initially 20 centimeters from the bottom in each arm. An immiscible liquid of density 4.0 grams per cubic centimeter is added to one arm until a layer 5 centimeters high forms as shown in the figure above. What is the ratio H2 over H1 of the heights of the liquid in the two arms? So, one thing that you should recognize before you start the problem, because you can confuse yourself. I've confused myself sort of with this problem as far as when I go to try and explain it. I want to sort of reach out and find some of the places where people might typically get confused and address those. But with a U-tube like this, no pun intended, with a U-tube, and you have water in there, one of the first things you have to recognize is if you total up the two heights, and you call that, in this case, 40 centimeters total. The one thing you just have to realize is that if you push down one end, if you push it down 1 centimeter, well, if this end goes down 1 centimeter, the other end must come up 1 centimeter. You still have a total, your two heights still equal 40. It kind of doesn't matter what the bottom of that tube looks like. I mean, this could have all kinds of crazy little loops and bulbs and whatever in there. Still, it would be the same thing. If you picked a reference point there and you pushed down on one end, it would still come up on the other end by the same amount. And you would still have a constant total height between whatever reference point you chose. The way they've set up this problem, it just happens to be the bottom there. That's the only way that I can see people getting confused on this problem. Otherwise, it's very straightforward. And so in my head, I'm just almost thinking of this thing as a scale and balancing out the two sides. I just multiply the density times the volume to get the weight of this immiscible liquid, but which incidentally, hopefully, more or less, that definition is just mean it doesn't mix. It doesn't mix in with the other, because if it mixed, then the volume, or yeah, the total height would change. It doesn't mix. So the way I see it is I have this immiscible liquid here, this dark stuff, and that's pushing down with some force, and to get that weight, I would just multiply the mass by gravity or whatever. And then on the other side, when this thing reaches equilibrium, I've got a column of water that's balancing that out. You know, I could probably try and remember fancy words like pressure potentials or something like that would be important to know, but in my head, this is the simple view of it. These two columns of liquids are pushing down with the same force at that point. Okay, that's the way I see it. A simplified view, to be sure. So the mass of the column multiplied by gravity, the mass of this column multiplied by gravity. The mass of this column is just its density times its volume. Its volume is its area times the height. And then this column is going to be the same. It's density times its area times its height times the gravity. And these, of course, are going to cancel out. And we just have the densities and the heights. So it gives us the density as 4 here. In this case, usually in a lot of cases, it's pretty slick to convert right to your standard units, kilograms and meters and whatnot. In this case, it's probably counterproductive to do so. You can just leave everything in centimeters and grams, and as long as both sides are both in centimeters and grams, you're just fine. So it tells us this height is, I think, 5 centimeters. Let me make sure. 5 centimeters high. So you just get 4 times 5 on this side, and here the density of water is 1 multiplied by the height of that water column. So right there, you just manipulate that around, but the height of the water column is going to be 20. So that's 20. This is 5. And that's all fine and good, but it does want the total. So have a look at that if you need any of that crap. And I'm going to erase it. If you need, because you need the total height. And so again, this is a simplified way of looking at it. But remember how I said you had 40 centimeters total of the water. And if you push down one side and it comes up the other, you still have 40 centimeters total of the water. So 20 centimeters of the water is tied up here. So there's got to be 20 more centimeters of water. And so it just makes sense to me that 10 of it is tied up here and 10 of it is tied up here. Maybe I'm just oversimplifying that, but well, you know, I guess that looks a little better. Okay, so and then there you kind of have it. I mean, there you get the ratio of the two heights. You want to make sure you get it right. It's h2 divided by h1, and this is h2. So my total height there, I would say, would be my 30 centimeters, and my total height here would be my 15 centimeters. And that would be the ratio between them. And so I want to look at my answers and see if I get something like 30 divided by 15. And I do not. But I can find the next best thing, which is looking like answer C, which is 2 to 1. Same ratio, right? And I would pick answer C. And so again, as long as I didn't think too much about this problem, it's pretty straightforward. It's really frustrating too. That's the answer. If you're done, close up the video. I do want to comment on this. Again, that's number 30 on the 96 exam. I believe this is kind of the only problem of its type. And that's an interesting idea that I looked at. I've looked at all of the mechanics problems that I could find for all 4 of the practice exams, and I didn't really see like a fluid statics problem like this. Maybe one other one with a balloon floating. And it's frustrating. It's frustrating to know that it can be on there, but it's maybe not that likely to be on there. Something like this. So of course you do need to study it. Anyways, because it could potentially be on there, but yeah, so it's kind of a common sense type of mechanics problem, I would say this one is. So hopefully that helps you out, and keep watching, and as always, study hard. Good luck.